Today we're going to be talking about a bunch of different tests for convergence. Some of these you have seen before, some of them you have not. We'll go through them, but we're going to keep repeating using them over and over and over again. So it's going to feel like a lot of information up front, but we'll continue to review these and go over them. All right, the first test for convergence, or in this case divergence, is the divergence test. This is a really simple one. Basically, if we look at the limit of the nth term, or in this case UK, if this doesn't equal 0, then you don't have a sum, which means the series automatically diverges. So here, if I look at the limit as k goes to infinity of k plus 1 over 3k plus 2, we get 1/3, which does not equal 0. So this series diverges. Okay, it's because what you're saying here is I'm adding an infinite number of 1/3. I'm going to have 1/3 plus 1/3 plus 1/3 plus 1/3, so it's not going to come to a value. The converse of this is inconclusive, or if you do get 0, it might converge, but it might still also diverge. Okay, let's look at the comparison test. This one we did in pre-calc as well. Let A of k and B of k be series with positive terms where A is less than or equal to B. So let me kind of illustrate this. So I've got a small series and a big series. Okay, I'm going to let that be my A's. And then a series that's bigger, B. Okay, if the bigger series converges, meaning it comes to a limit, that means the smaller series also has to converge. If the smaller series diverges, which means it's not going to come to a limit, and these all have positive terms, so that's an important part. If this diverges, that means it's just going to keep growing and growing and growing, which means the bigger one also has to diverge. So we're going to do an investigation on the harmonic series. The harmonic series is 1 over n. So I'm going to do a comparison, and I'm going to do a comparison with the harmonic. So I'm going to write out the first 16 terms of the harmonic series. I'm going to pause while I do this. So there are the first 16 terms of the harmonic series. I'm going to compare that to what I'm just going to call series 2, which is going to start with a 1, then a 1/2, then 2 1/4, then 4 1/8, and the rest of these are going to be 1/16. So this mystery series, if we look element by element, we're the same here, the same here. 1/3 is bigger than 1/4, 1/4 is the same. 1/5 is bigger than 1/8, 1/6 is bigger than 1/8, and so on. So the harmonic series is my big series. This one is my small series. So let's investigate this random series that I threw together. If we group the numbers with the same denominator, we've got 1 plus 1/2. 1/4 plus 1/4 is 1/2. 4 1/8 is 1/2. And all of these 16s add up to 1/2. Well, I'm adding an infinite number of 1/2, so that series is just going to keep growing bigger and bigger and bigger, which forces the bigger series to also diverge. So this is counterintuitive, but the harmonic series (1 over n) always diverges. So we can use that now. All you have to say if you have this series is that it's harmonic, therefore it diverges. The next one is the integral test. This one is new to you. There's 3 conditions that need to be met. If the series is positive, decreasing, and continuous, then if we have some series, we're going to rewrite the general term and put it in an integral. So we're going to let g of x equal the general term in the sigma notation, and we're going to integrate from 1 to infinity. Either you're going to get a value, which means the integral converges, which means the series is going to converge, or you're not going to get a value. If the integral diverges, then the series diverges. The key to this one is if you have something that is easy to integrate, then you can use the integral test. So we're going to use the integral to determine the convergence of something we already know, the harmonic series. So we're going to do the integral from 1 to infinity of 1 over x dx. So we'll look at the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. Well, the integral of 1 over x is natural log x. So we're looking at the limit as b goes to infinity of natural log of b minus natural log of 1. Well, if we're going to infinity, this is going to go to infinity. And natural log of 1 is just 1. So this equals infinity, which means it diverges, which means both diverge, which we already knew, but we can prove that simply with the integral test. Next is a p-series. So the p-series is 1 over n to the p, some power. There's 2 conclusions. If p is greater than 1, then the series is going to converge. So if you've got 2, 3, 5, the series is going to converge. If it's between 0 and 1, including 1, which would make it the harmonic series, it's going to diverge. So I'm going to do a quick proof for you using the integral test. And you actually have done this on one of your tests. Okay, so I've got this, which is the same as x to the negative p. That way we can think about it as using the power rule. So we're going to integrate this and leave space for the constant. So we're going to have x, we're going to add 1 to this exponent, and then I'm going to divide by that new exponent. And we're evaluating this from 1 to b. This part's not going to really matter. This is the important part here. Okay, we're trying to decide what values of p will make this converge versus diverge. Well, we have a negative exponent here. So if p is between 0 and 1, that means this exponent is going to be greater than 0. Okay, which means this is going to go to infinity. It's just, if this is a positive exponent, it's just going to grow. But if p is greater than 1, that means negative p plus 1 is less than 0, making this exponent negative, which means when we go to infinity, we're going to 0. All right, so now that we have the P series, we just need to apply it. So this is k equals 1 to infinity of 1 over k to the 4/3, which means P is 4/3, which is bigger than 1, which means our series converges. Here, this is the same as k to the 1/4, so P is 1/4, which is less than 1, which means the series diverges. Here, P is 5/3, bigger than 1, so our series converges. Pi. Pi is bigger than 1. So it converges. This one here, this is just the same as saying 7 for k plus 5 to the p. So p we don't know, so this one's going to converge. If p is greater than 1, it will diverge. If p is between 0 and p1. Convergence theorem is just kind of an aside. If you know you have a convergent series, then the terms have to go to 0. The converse of this is not true. If the limit is 0, it can converge or it might diverge, like in the harmonic series. Now we've got some problems where we're going to determine the convergence. So we need to pick a test. This one here, if we look at this, that's going to be pretty easy to find the integral of. So I'm going to use the integral test. Okay, and I'm going to do a u substitution here. I'm going to let u equal the denominator. And du is going to equal 2x dx. I'm going to put a 2 in here, which means that I need to undo that and do the u substitution. Okay, so now we have du over u. I can integrate this. And I'm just going to pull this 1/2 out of everything. So this is going to be the natural log of the absolute value of u, evaluated from 1 to b. I'm going to go back to the x's, although that's not really going to change much. Because they really have natural log of x squared plus 1, which we're going to evaluate from 1 to b. So we're going to have the natural log of b squared plus 1 minus natural log of 2. Well, if we're going to, as b goes to infinity, the natural log, this is just going to grow and grow and grow. So since this integral diverges, both of these diverge. Diverge. We'll learn how to spell. Next one is another one that's pretty simple to integrate. Because we know that the integral of 1 over x squared plus 1 is tangent inverse. All right, so we've got the limit as b goes to infinity of tangent inverse of b minus tangent inverse of 1. Well, tangent inverse of b goes to pi over 2, because remember the graph of that goes like that. So it always has an asymptote at pi over 2. So this is going to be pi over 2 minus tangent inverse of 1 is pi over 4, which is pi over 4. We don't really care. What we care about is we got a value, which means this converges, which means both series and integral converge. This next one, both of these series are infinite geometric series. So if I have an infinite geometric series with a common ratio between -1 and 1, then it converges. So this one converges and this one converges. So let's go ahead and find the sum. So this one's a1, if I plug in 1, is going to be 2/5 over 1 minus its common ratio is going to be 1/5 because the 2 isn't in the parentheses. Minus, if I plug in a 1 here, we're going to get a 3 over 2 to the 0, which is just 1. So 3 over 1. 1 minus our common ratio is going to be 1/2. So we're going to have 2/5 over 4/5 minus 3 over 1/2. So 2/4 minus 6. So we're going to get a -5.5. But we just have an infinite geometric plus an infinite geometric, so this is convergent. 2 over k. Harmonic divergent. Okay, so I have a series 1 over n squared, which does converge from the p-series test. We're going to look at some partial sums. Mostly the reason I put this here is just to show you that you can do them in your calculator. If you go to alpha f2, where you live to do your integrals and your derivatives, there is a summation there, which will give you the sigma notation. So I'm just going to say we're doing 5. So x equals we'll do 5 of 1 over x squared. And that's going to give me my values. So we can do that to find a finite sum. So we can repeat that for 10 and 20. The graph you could do them all individually, but in general, it's just going to approach that pi over 6, or pi squared over 6, and go like that. Okay, let a sub n, b sub n, c sub n be sequenced with positive numbers, such that the positive numbers a is less than b is less than c. If c converges, which statement must be true? If c converges, well, a can't diverge, because it's less. B needs to converge because it's smaller. And a plus b diverging, nope, that can't happen either. Because they both, if c converges, then a and b both have to converge. Okay, the next one says if the series 1 over n to the 2a converges if and only if. So this is a p-series, which means we need 2a to be greater than 1. We need that power to be greater than 1, not equal to 1, because if it equals 1, it's harmonic, which is divergent. So we need a to be greater than 1/2. So it's that one. It's not inclusive and not equal and not bigger. Okay, this next one quick thing. This should say none, and this should be 1 and 2. Anyway, so which of these converge? 1 over n, harmonic, divergent. The other two, whenever you have a natural log in 1 over n, we know we can integrate that with a simple u substitution. So I'm going to look at the integral from 1 to infinity. Since this is a multiple choice, and this will be the case with a lot of the series ones, is it'll be like this. You're not actually going to have to show the test, you just have to be able to do the test. So I'm going to let u equal natural log of x, which means du equals 1 over x. So this is now the integral from 1 to infinity of u du, which is 1/2 u squared from 1 to infinity. Well, if I plug in 1 infinity here, this is going to diverge. Okay, this one's going to be pretty much the same with a squared. Ln squared x u equals ln x du equals 1 over x. So we're going to have x squared dx, which is 1/3 x cubed from 1 to infinity, which again, if I plug in infinity, that's just going to get bigger and bigger. So this one diverges also, so none converge. So my point is, the level of work you show is really what you need to perform this. Next, we have the ratio test. The ratio test, we're going to look at not the nth term, but we're going to look at the nth plus 1 term over the nth term. So we're going to take the general term, add 1 to the k, we're going to look at the next term and get that ratio. If that limit is smaller than 1, the series is convergent. If the limit is bigger than 1, the series is divergent. And then if it equals 1, the test fails. We're going to use this with products, powers, and factorials, and as we go through the examples, you'll see why. All right, so we're going to have the limit as n goes to infinity of the nth plus 1 term, so 2 to the n plus 1 over n plus 1 factorial over 2 to the n over n factorial. All right, I'm going to rewrite this 2 to the n times 2 to the 1. I'm going to rewrite this n plus 1 factorial as n plus 1 times n factorial, because if I were to keep, if I had 9 factorial, I could write that as 9 times 8 factorial. And then copy dot flip on the next one, aka multiply by the reciprocal. So the 2 to the n's go away, the n factorials go to the right. So this will always happen with factorials, it will always happen with the exponentials, they're always going to simplify this way. So we're going to have 2 over n plus 1 is what is left. That limit is 0, which is less than 1, which means our series converges. Okay, so I will point out what that means is n factorial grows faster than 2 to the n. Now let's look at one more, or another one. So we have n to the n. So we're going to have the limit as n goes to infinity. The nth plus 1 term here is going to be n plus 1 to the n plus 1 over n plus 1 factorial all over n to the n over n factorial. All right, so this numerator I'm going to split up just like I did with the 2's. So this will be n plus 1 to the n times n plus 1 to the 1 over n plus 1 times n factorial times n factorial over n to the n. So we get rid of the n plus 1, we get rid of the n factorial. So what I have left is n plus 1 to the n over n to the n. So what do we do with that? Well, they're both to the same power. So I can rewrite this as n plus 1 over n to the n, which you might recognize in this form, or n over n is 1. So we get 1 plus 1 over n to the n, which has come up in really random locations, but it will continue to come up quite frequently. This is e. 1 plus 1 over n to the n is the value e. E is bigger than 1, which means this series diverges. Okay, going back to what that means, n to the n grows faster than n factorial. Do another one. So we're going to have n plus 1 over 2 to the n plus 1 over n over 2 to the n. Okay, again, anytime I've got that exponent, I'm going to rewrite it like that. So we can get rid of the 2 to the n's. So I have n plus 1 over 2n, which is 1/2, which is less than 1, which is convergent. All right. So we're going to have 1 over 2 times k plus 1 minus 1 over 1 over 2k minus 1. Okay, so when I multiply by the reciprocal, we're going to have 2k minus 1 on the top. In the bottom, this is going to be 2k 2 minus 1, so 2k plus 1. Well, this limit is 1. And if we get 1, the test is inconclusive. So polynomials don't really work with the ratio test. Same with things like logarithms that grow too slowly. So products, powers, exponentials, those work good, but polynomials really don't. The last test we're going to talk about today is the root test. We're going to take the square root of the general term. And if that is, we're going to look at the limit. If that limit is less than 1, it converges. Bigger than 1, it diverges. Equals 1, it fails. So this pairs with the ratio test. You want to use it when you have things with powers, kth powers, like here. So we're going to look at the limit as k goes to infinity of our general term e to the 2k over k to the k. And rather than writing it as the kth root, I'm just going to write it as 1 to the 1 over k. So if I have e to the 2k to the 1k, that's just going to be e to the 2. If I have k to the 1k, that is just k. Well, if we go to infinity, that goes to 0, which is less than 1. So this is convergent. Same thing here. Okay, I've got a kth power, so let's take a kth root. So we're just going to have 1 over the natural log of k. And as we go to infinity, that's 0, less than 1, convergent. This one's pretty simple. We're just going to take 2k over k plus 1 to the k to the 1/k, so the exponents go away. Which is 2, which is bigger than 1, so this one is divergent. Alright, warning on this one's going to be kind of long, so stick with me. Alright, so I'm going to take k over 5 to the k and raise it to the 1 over k, which is fine for the bottom, but in the top, I'm left with k to the 1 over k. So this will be 1/5 of whatever the limit k goes to infinity of k to the 1 over k. Okay, I need to deal with this limit, and a long time ago we dealt with limits like this. So I'm going to take this and deal with the k to the 1 over k separately, then we'll come back over here. So I'm going to let y equal k to the 1 over k. Then I'm going to take the natural log. Because what that allows me to do is pull this down. Okay, so how does that help me? Well, we're trying to find the limit as this goes to infinity, and then I can transfer that to k to the 1 over k. So I'm going to look at the limit as k goes to infinity. This is natural log of k over k. The good news is this is infinity over infinity, which means we can use L'Hopital's rule. So we're going to 1 over k over 0, sorry, over 1, which is just 1 over k. So the limit as k goes to infinity of 1 over k is 0. Well, that's what this is going to. So that means the natural log of y is going to 0. So e to the natural log of y is going to e to the 0. It means y goes e to the, wrong color, e to the 1, e to the 0 is just 1. So y is going to 1. So this is going to 1. So this is going to be 1/5 times 1, which is 1/5, which is less than 1, which means it converges. Now, in all likelihood, if you look at this and you've got k over 5 to the k, the exponential is going to grow significantly faster. So it will converge, but this would be the proof for that. Okay. Here, which of these converge? 1 over 1 minus 5/4, this is really negative 1/4 to the n, which is an infinite geometric, so it converges. N to the n over n factorial we did just recently. This grows a lot faster, so this one does not. And this is just the sum of e, which is going to diverge. So it's 1 only. So that was a lot of information, but like I said, we're going to continue to use these tests over and over and over again to reinforce them.